Imagine waking up to a headline that instantly freezes the world. A black hole is on a direct path toward Earth. At first, everyone assumes it's fake. Then observatories across the globe confirm the impossible. Panic spreads. Markets crash. Millions look to the sky, searching for an enemy they'll never see. Because that's the terrifying truth. A black hole is completely invisible. Now, one thing is important. This scenario is fictional. There is no known black hole heading toward Earth today. But every consequence you'll see in this video is based on real physics and our best scientific understanding. Black holes aren't cosmic vacuum cleaners. They're regions where gravity becomes so extreme that even light cannot escape. Near them, space bends, time slows, and reality behaves in ways that seem impossible. And if Earth ever began falling toward one, our last moments wouldn't start with an explosion. They would begin with something so subtle that most people wouldn't even realize the end had already begun. But if a black hole is invisible, how would humanity know it was coming? How do you detect something that doesn't emit light, reflect light, or leave a visible trace in space? You don't search for the black hole. You search for its fingerprints. Most black holes are born when massive stars exhaust their nuclear fuel and collapse under their own gravity. The remaining core becomes so dense that it forms a region where gravity is overwhelming. Surrounding it is the event horizon, a boundary beyond which nothing, not even light, can escape. Despite what movies often suggest, black holes aren't giant cosmic vacuum cleaners wandering through space, pulling in everything around them. If our sun were magically replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does today. The danger comes only when you get too close. Astronomers find black holes by watching nearby stars orbit invisible objects, detecting superheated gas glowing as it spirals inward, and observing light bending around unseen gravity. A black hole may be perfectly invisible, but its gravity always reveals its presence. And if one ever entered our solar system, those invisible fingerprints would soon become impossible to ignore. A black hole wouldn't have to reach Earth to begin destroying everything we know. Long before our planet came anywhere near it, its gravity would start pulling at the solar system itself. Exactly how severe the effects became would depend on the black hole's mass and the path it followed. But if it passed close enough, nothing would remain untouched. Mercury could be the first to drift from its ancient orbit. Mars might slowly wander off course. Far beyond Neptune, billions of frozen objects in the distant Oort cloud could be disturbed, sending enormous comets hurtling toward the inner solar system. Then, Earth's orbit could begin to change. Even a small shift would be catastrophic. A path slightly closer to the Sun could scorch the planet. A wider orbit could bury it beneath endless ice. Seasons would lose their rhythm. Weather would become increasingly violent. Entire ecosystems could collapse before humanity ever understood what was happening. Because before anyone saw the black hole, the solar system itself would already be telling us that an invisible force had begun rewriting its destiny. And soon, that same force would stop moving planets and start tearing Earth apart. At first, nothing would seem different. The ground beneath your feet would still feel solid. The sky would still look familiar. But gravity would no longer be equal. As Earth moved closer, the side of our planet facing the black hole would experience a slightly stronger gravitational pull than the side facing away. Scientists call this a gravitational gradient. At great distances, the effect would be almost impossible to notice. But with every passing hour, it would grow stronger. The oceans would begin rising in ways no tide on Earth has ever done before. Coastlines would disappear beneath walls of water. The planet's crust would groan under immense stress, triggering earthquakes and volcanic eruptions on a scale beyond recorded history. The atmosphere itself would become unstable. Jet streams would twist into violent new patterns. Storms would merge into continent-sized systems. Humanity wouldn't be fighting the black hole. We would be fighting the gravity it unleashed. And this was still only the beginning. Because the closer Earth fell, the stranger reality itself would become. If gravity can bend space, it can also bend time. This isn't science fiction. It's one of the most extraordinary predictions of Einstein's general theory of relativity, confirmed by decades of scientific experiments and even accounted for in technologies like GPS satellites. The stronger the gravity, the slower time flows. As Earth drifted closer to the black hole, every clock on the planet would begin ticking ever so slightly slower than clocks far away in deep space. At first, no one would notice. A heartbeat would feel the same. A conversation would end in the usual time. The sun would still appear to rise and set. Life would continue as if nothing had changed. But somewhere far beyond the black hole's immense gravitational pull, an observer watching Earth would witness something astonishing. Our planet would appear to move more and more slowly. Every wave, every heartbeat, every passing second would seem stretched beyond imagination. As Earth approached the event horizon, its light would become increasingly red, dim, and delayed, until it appeared almost frozen in time. Yet for everyone still on Earth, nothing would feel unusual. Because while the universe watched us slowly disappear, we would keep moving toward the black hole, completely unaware that,
if Earth wandered
to everyone
too close
else,
to a black hole,
time itself
gravity would
had
twist
nearly
space
left us
itself,
behind.
bending light.
Until now, Earth had been fighting gravity as a planet. But that was about to change. Because near a black hole, gravity doesn't pull equally. The side closest to the black hole feels a stronger pull than the side farther away. Scientists call these tidal forces, and they grow stronger with every kilometer you fall. For Earth, the consequences would be unimaginable. The planet would no longer remain perfectly round. Its oceans would begin stretching toward the black hole. The crust would crack under impossible stress. Mountains would collapse. Entire continents could slowly deform as gravity pulled one side harder than the other. And the same force acting on Earth would act on every living thing. If the black hole were small enough, those tidal forces could become overwhelming even before reaching the event horizon. The pull on your feet would be stronger than the pull on your head, gradually stretching your body farther and farther apart. Scientists have a name for this horrifying process: spaghettification. It sounds almost humorous, but it's one of the most terrifying consequences predicted by modern physics. And unbelievably, the worst part still wasn't crossing the event horizon. It was what waited beyond it. For generations, people imagined the event horizon as a giant cosmic wall, a place where everything ends in an instant. But reality is far stranger. If the black hole were supermassive, the event horizon itself might look surprisingly ordinary. There would be no solid surface to strike, no sudden flash, no invisible barrier blocking your path. You would simply keep falling. By the time you crossed that invisible boundary, escape would already be impossible. Even light, the fastest thing in the universe, could no longer find a path back out. To you, time would continue normally. Your heartbeat, your breathing, your thoughts. Everything would feel almost unchanged. But to an observer, watching safely from far away, you would appear frozen forever at the edge of the black hole, your image becoming dimmer, redder, and fainter until it slowly vanished from sight. The most terrifying part, you wouldn't know the exact moment you crossed the point of no return. Because the event horizon isn't a physical wall, it's a boundary written into the geometry of space-time itself. And beyond that boundary, our current understanding of physics begins to fade. What lies deeper inside the black hole remains one of the greatest mysteries in the universe.
Beyond the event horizon, there is no turning back. Every possible path through space, and even through time, for a while, if the black hole is supermassive, you might not notice anything extraordinary. But that illusion cannot last. With every passing second, the tidal forces become unimaginably stronger. The difference in gravity between your head and your feet grows so extreme that no material in the universe, not steel, not rock, not even an entire planet, can resist it forever. Earth would be torn apart. Mountains would become dust. Oceans would unravel into endless streams. The planet itself would stretch into a glowing ribbon of rock, metal, and plasma, spiraling helplessly toward the center. Eventually, everything that once made Earth recognizable would disappear. And ahead lies the singularity, a point where, according to general relativity, matter is crushed into an unimaginably tiny region of space. But here's the truth. No one knows what actually happens there. Our best theories break down before reaching that point. The laws of physics that explain stars, galaxies, and even black holes themselves can no longer describe what comes next. The universe simply stops giving us answers.
Everything you've seen so far is supported by our best understanding of physics. But beyond this point, science enters the unknown. According to Einstein's general relativity, matter continues collapsing toward the singularity, a region where density and the curvature of space-time become infinite. Yet, infinity is nature's way of telling us that our equations are no longer complete. This is where two of the greatest theories ever created begin to disagree. General relativity describes gravity on the largest scales. Quantum mechanics governs the smallest. Inside a black hole, both should apply, but they refuse to work together. Some physicists believe a future theory of quantum gravity may reveal what truly exists beyond the singularity. Others suspect the singularity itself may not physically exist as our current equations predict. For now, no experiment has reached that place. No signal has ever escaped it, and no human knowledge extends beyond its edge. The greatest mystery isn't what a black hole destroys, it's what it hides. And perhaps the most terrifying truth of all is that the universe may never allow us to find out. Black holes are often described as the universe's greatest destroyers, but perhaps that's the wrong way to think about them. Without black holes, galaxies including our own Milky Way might never have evolved the way they did. Supermassive black holes sit at the hearts of most large galaxies, quietly shaping their growth over billions of years. They are not monsters. They are part of the architecture of the cosmos. If Earth were ever to fall into one, our story would end. But the universe wouldn't even pause. Stars would continue to be born. Galaxies would keep colliding. And somewhere, light would still be crossing the darkness between worlds. The truth is, a black hole doesn't just remind us how fragile our planet is, it reminds us how little we truly know. Every answer we've discovered has opened the door to even greater questions. And maybe that's the most beautiful part of science. Not that it explains everything, but that it constantly reveals how much more there is to explore. So the next time you look up at the night sky, remember this. Somewhere out there, invisible to every human eye, black holes are silently shaping the universe, waiting for us to understand them. Until then, they remain among the greatest mysteries humanity has ever faced.